Hello, in this video I will discuss Lab 5, Magnetic Braking with Faraday, in which we examine how a magnet falls through a metal tube. The objective of this lab was to determine the time required for a magnet to travel through an aluminum tube, using both an experimental method and a computational model. Some important equations and constants we used to do this include the PHYS law, which was used to calculate the magnetic field of the magnet, along with the magnetic flux, which can just be calculated by multiplying the magnetic field by the area, since the area is constant, along with Faraday's law, which states that the voltage produced equals the change in magnetic flux over the change in time. To collect the experimental data for this lab, we used a magnet with a known magnetic dipole from a previous lab, along with a tube of aluminum foil whose dimensions we measured, and then drop the magnet through this tube of aluminum foil while recording it each time. We then used the timestamps from these recordings to determine the exact time it took for the magnet to travel through the tube, and we performed this 5 times in order to determine the average time it took for the magnet to travel through the tube of aluminum foil. During the lab, it was observed that the magnet slows significantly as it travels through the tube compared to an outside of the tube. This can be linked to Faraday's law, which, as described previously, states that a change in magnetic flux will result in an EMF. The magnet generates a change in flux over time as it travels through the aluminum tube. This in turn results in an EMF and an induced current through the tube, and this induced current in turn creates a magnetic force on the magnet in the opposite direction of its motion. Ultimately, this results in the magnetic force acting in opposition to the gravitational force, causing the magnet to slow as it travels through the tube. Our experimental results from the lab can be found below. The average time it took for the magnet to travel through the tube was 1.305 seconds. The magnetic moment of the magnet, which we recorded in the previous lab, was found to be 3.487 amperes meters squared. The magnet mass was found to be 0.025 kilograms, and the tube length was determined to be 0.3048 meters, while the tube inner radius was 0.02 meters, and the tube foil width was 0.0065 meters. For the magnet to travel through the aluminum foil tube. In this first part, you can see some of the different experimental constants we used within the computational model, along with a function to calculate the magnetic field of the bar magnet using Biot-Savart's law. On this slide, you can see a function used to calculate the magnetic flux through each imaginary ring of aluminum foil, along with the gravitational force acting on the magnet and the current traveling through each imaginary ring of aluminum foil. On this final side of the computational model, you can see where the magnetic force acting on the magnet is calculated, along with the net force calculations. And then finally, you can see how these net force calculations are in turn used to calculate the actual velocity of the bar magnet and the position of the bar magnet. On this slide, you can see the computational model results, which include a graph of velocity versus time, along with a visual which shows the magnet actually traveling through the tube, and the time in the tube, which was calculated to be 1.535 seconds. In the visual from the previous slide, the red rings represent current moving counterclockwise, while blue rings represent current moving clockwise. If the magnet were to be flipped, then these colors would also flip due to the change in direction of the current flow. Nothing would change in the physical system, however, as the forces would be the same. The magnet took less time to travel through the tube in the actual experiment than in the computational model. This could be due to the fact that the cardboard tubing may interfere with the magnetic forces which act on the bar magnet. This would thus decrease the time spent in the tube compared to the idealized computer model. The graph from the previous slide shows that the magnetic force increases over time until the bar magnet reaches a constant velocity at the middle of the tube. At this point, the gravitational and magnetic forces are equal. The magnetic force then proceeds to decrease as the magnet approaches the other end of the tube. The resistivity of the conductor reduced as close as possible to zero, then the induced current and the magnetic force acting on the bar magnet would increase significantly due to the greatly decreased resistance. This would in turn result in the velocity of the magnet in the tube being much slower, since the magnetic force acting on the bar magnet would be much stronger. If holes or slots were cut into the tube, then this would prevent current from flowing at certain points in the tube due to gaps being present in some of the rings. This would in turn decrease the magnetic force experienced by the bar magnet, since some parts of the tube wouldn't have an induced current.